Hello, welcome to Proximity Math here. Today we're gonna do a problem which involves um, a very fun roots of unity manipulation. Okay, so if we have a regular heptagon inscribed in a unit circle, well, okay, it's a unit circle. So this is radius 1, right? Okay, so the heptagon, it has 7 points. It's a 7-sided polygon, basically. It would look like this. Okay, these are its points. They're A, B, C, D, E, F, G. Okay, so it's asking us to compute the value of the sums of the squares of the distance. The sum of the squares of the distances from A to the other points. So we're gonna have AB, AD, AC, and so on. Okay, the first thing to notice about this is that first thing, notice that since it's a regular heptagon, it's gonna be symmetric about this line that passes through A. So the diameter that passes through A, it's going to be symmetric about that line. There's 3 points on this side, 3 points on this side, and then A, meaning the sum, like the sums of the distance, squares of the distances. So AB, AC, and AD squared, they have the same sum as AE, AF, and AG because it's symmetric. So our sum is actually equal to AB squared plus C squared plus AD squared. Okay. So now, how do we find these? Well, we can apply roots of unity. Since this is a unit circle, these points are, well, if we let the complex number W be, for example, cis of 2 pi over 7, because it's a heptagon, then this is, which is also e to the I 2 pi over 7. Okay, this, if you use complex numbers to represent the points, B is going to be omega, sorry. C is omega squared because it's 2 rotations around it. And D is omega cubed. So this really boils down to, well, the distance squared is just the absolute value squared. The absolute value of 1 minus omega squared, the distance squared, okay. And it's omega to the k. I'm making this in some notation. To the n, sorry. N equals 1, and it goes through 3. Okay. So this is just the sum, same thing as the distances, the square of the distances, because we have these 3 points. Okay, so now this sum given omega, well, we have the absolute value. If you have a complex number, its absolute value squared, this is a well-known factor, is equal to it times its conjugate. Okay, now we would have also, since for any root of unity, for example omega in this case, its conjugate is going to be symmetric about the real axis. This is the reverse rotation of omega. It's a reverse rotation of 2 pi over 7 radians, which means this is equal to omega to the negative 1, omega to the negative 2, and omega to the negative 3. So the conjugate in this case, so we have, if we have 1 minus omega to some power, and its absolute value squared is going to equal, using this formula above, 1 minus omega to the n times its conjugate. This is the real part. I mean, 1 is real, so it's conjugated is itself. And then this becomes omega to the negative n, which is 1 minus omega to the omega to the n minus omega to the negative n, and finally plus, well, these multiply out to 1 and the exponents cancel, so we're adding 1, and this is just 2 minus omega to the n minus omega to the negative n. Alright, we have this really nice formula we can use on this absolute value squared. Okay, now this gives us twice of n ranging 1 through 3, the sum of the distances squared. Using this formula, we have okay, if we're summing from 1 through 3, then we're multiplying 2 by 3 because we're summing 2 3 times. So 6 minus, and then these always have negative signs, so we can just add them. We have for n equals 1, these, and since this is a root of unity, this, we can loop this around, and omega to the negative n is actually omega to the 7 minus n. Because it's a 7th root of unity, omega to the negative 1, for example, is omega to the 6th, and counterclockwise way. So what we actually get are these pairs that sum to 7. And it's really neat. Okay, that's the summation from n going from 1 to 3. Okay, so now we have 2 times, well, I can take the 6 out, minus 2 times, okay, and this is the last step. Notice all these powers are from 1 to 6. We have exactly 1 each. And an extremely well-known factor, or actually you can use a geometric series or factorization. We would have omega to the 7 minus 1 in this case over omega to the omega minus 1. This, you can use an algebraic factorization. You would get omega to the 1 plus omega to the 2 plus, actually it starts at 1 plus omega to the 1 plus blah, blah, blah. Using an algebraic factorization again, we get this sum, which we're finding right here, except for the one term. Okay, so if we let this be s, for example, this sum be s, so we have s over here, then s is just these 6 terms. And if you look over here, omega to the 7th, it's a root of unity, so it's going to be 0. And this is also a well-known fact about roots of unity too. The sum of the power sum 0 through n minus 1, where it's the nth root of unity, will be 0. So take 1 for both sides, you get -1. S is actually -1. Okay, and now we can simply add this and get 12 plus 2 equals 14 as our final answer. Thanks for watching, and I hope this helped you.